G'day, welcome to our final lesson in this current unit on chemical bonding. Today we are looking at bonding and the physical properties that result as a consequence of the type of bonding that is present. Our lesson objective is we're going to identify and rationalize the types of intermolecular forces a molecule will have and consequently describe and predict the physical properties of different species based on the type of bonding that is present. As always, the outcomes we will be addressing today. So, last lesson, we introduced the different types of intermolecular forces that are present. We had our dipole-dipole and our hydrogen bonding, our permanent intermolecular forces where we have electrostatic attraction between a partial positive and a partial negative charge. And then we had our van der Waals, which was when we have no polar bonds in a molecule or we have no overall polarity in a molecule. And we have temporary dipoles that form based on the random distribution of electrons around an atom or a molecule. So we're going to go into that in a bit more detail today, specifically looking at how this affects the different physical properties that compounds and species might have, such as their boiling point, their melting point, their reactivity, their solubility, their electrical conductivity, things like that. So we finished off at the end of the last lesson looking at van der Waals forces, so that's what we might pick up on today. So we said van der Waals forces were the weakest intermolecular forces that are present, and it's just due to a temporary dipole that will randomly form, and then that can have a sort of knock-on domino effect to form other temporary dipoles in other species. If you need a refresher on that, previous video is there for you to go over. But let's have a look at how the size of the van der Waals can change. So the van der Waals are our weakest intermolecular force, but they will increase with the number of electrons in the molecule. So the more electrons that you have, the more van der Waals interactions you will have, because that temporary dipole that can form, if you've got more electrons, and if there's more electrons on one side to the other side, that temporary dipole will have a larger magnitude, it will have a larger charge. So we can see this very clearly when we look at the boiling points of our noble gases. Our noble gases are our group 18 atoms. They have a full valence shell and they just exist as monoatomic atoms. So if they're monoatomic atoms, they can't have any sort of polarity within them. Pardon me. They can't have any sort of polarity within them. So they will just have van der Waals forces present. So we can see here we have the boiling point. Our smallest group 8/group 18 atom is helium, and we have the lowest boiling point there consequently. If we go down a group and we have neon as the next smallest noble gas that is present, we have more electrons in the helium, but less electrons than the next one, which is argon. That would be argon there. So our neon will have more van der Waals forces because it has more electrons than our helium, so it'll take more energy for it to boil as a result of that. Then we see our next one, we see the increase from argon to krypton to xenon, etc. So this really demonstrates that more electrons mean stronger van der Waals forces, because if you are boiling a certain substance, then you are disrupting the forces that are holding them together. In the case of our noble gases, the forces that are holding them together are the van der Waals forces. So the more electrons, the more van der Waals forces, the more energy you need to put in order to boil it. Consequently, the larger the boiling point that will be observed, which is what we see on this graph. So van der Waals forces increases with the number of electrons. They also increase with the number of contact points. So we can consider a molecule, C5H12. There are what exists isomers of this molecule. This term isomer we're going to look at long down the track, but just for now, if I draw two different molecules that have the same amount of electrons, so they've got 5 carbon atoms and they have 12 hydrogen atoms. So we have the same amount of electrons in both of these species that I'm going to draw. The first one is pentane, where we have our 5 carbons all in a row like that, and then our 12 hydrogens just branching off it like that, filling in all the hydrogens. The second molecule, which still has the molecular formula C5H12, but it has a slightly different structure, it's an isomer of this, is 2,2-dimethylpropane, and that will look like this. So it's still C5, it's still H12, it's just a slightly different arrangement of the atoms relative to one another. So if we look at the relative boiling points of these two molecules, pentane has a boiling point of 36.1 degrees, whereas 2,2-dimethylpropane has a boiling point of 9.5 degrees. And we can rationalize that based on what are called these contact points. So I've just redrawn this a slightly different way to help illustrate this a little bit better. So both C5H12, however, if we had, say, two molecules of the pentane here interacting, we could essentially get contact points between each of these little sections of the molecule. So we could have a sort of van der Waals interaction there, van der Waals interaction there, van der Waals interaction there, there, and so on. However, with our 2,2-dimethylpropane, because of the way the structure is a little bit more compact, it doesn't allow as many contact points to exist. Really, you could only have a contact point sort of between the two parts here. So you could have a contact point, van der Waals interaction there, contact point, van der Waals forces there. And this is what you see reflected in the boiling points. So pentane, that has a number more contact points, has a boiling point of 36.1 degrees Celsius, whereas our 2,2-dimethylpropane is a boiling point of only 9.5 degrees Celsius. So what affects our van der Waals forces? The number of electrons in the molecule and the number of contact points. Let's look at our dipole-dipole interactions. Generally, we said they are stronger than van der Waals forces, and that's because we have this permanent dipole that forms due to the unequal sharing of the electrons in a covalent bond. So one gets a partial, a delta positive charge, one gets a partial, a delta negative charge, and you have that electrostatic attraction between positive and negative, having it be a force of attraction. Stronger force of attraction between electrostatic delta positive and delta negative means more energy required to break them apart, consequently more energy to melt or boil them. And we're going to see that in some data. Example of pentane again, which has a boiling point of 36.1 degrees Celsius, and pentanal, which is a slightly different molecule, has a boiling point of 103 degrees Celsius. If I go back to the whiteboard and draw both of these, we will see this. So pentane was the same one as before. We have C5H12, whereas our pentanal is a little bit different. It has this sort of group like that on the end. Still got 5 carbons. However, we have this oxygen-hydrogen functional group that exists at the end of the chain there. So we can see our pentane over here. We have all non-polar bonds. Carbon and hydrogen have a very, very similar electronegativity. These are all non-polar bonds, so this will be a non-polar molecule. Conversely, our pentanal, we have all of these are non-polar bonds. However, down here we have oxygen that has a higher electronegativity than carbon. Remember, it's all to do with the position relative to fluorine on the periodic table. So if we have our oxygen, which is closer to fluorine than our carbon, it's going to have a partial negative charge. It's going to hold that electron pair closer to itself. So this is a delta negative, this is a delta positive. We get a dipole down here. So we end up with a very clear sort of non-polar end, but we have a very clear delta negative end and delta positive end. So we do have a polar molecule here. What that means is that this non-polar molecule will have only van der Waals forces, which are weak, they're the weakest, whereas our polar molecule here will have dipole-dipole interactions, and that's what we see reflected in the boiling point. Pentane has a much, much lower boiling point than pentanal, because pentane only has the van der Waals forces, whereas pentanal, much higher boiling point, it will have the dipole-dipole interaction. Again, illustrating that it's a stronger force of attraction, it's a stronger intermolecular force. Then we had our strongest intermolecular force, which was our hydrogen bonding, which was really sort of a unique case of dipole-dipole interactions. This is where we have the highly polarized delta positive on a hydrogen that has been covalently bonded with nitrogen, oxygen, or fluorine, because these three atoms are particularly electronegative, so they hold that electron pair particularly close to it. And this can form a very strong electrostatic force of attraction between the lone pair of electrons on the neighboring nitrogen, oxygen, or fluorine. So it's stronger than the dipole-dipole interaction, not quite as strong as a full covalent bond, about 1/10 of the strength. And we can see this in an example as well if we draw some more molecules. For example, propanol and one propanol. So one of these can have dipole-dipole forces, the other one can have hydrogen bonding. If I draw my propanol, it will look like this. Nope. That's propanone. Let's try that again. My propanol looks like this. That functional group at the end of the molecule. And then 1, 2, 3. Whereas our propanol looks like this. Similar, but a little bit different. It has this OH instead of just this double bond O. We fill in the rest of the molecule, the rest of the chain looks the same. So, in both cases, we have polar bonds. We have a delta negative and a delta positive here. Over here, we have a delta negative and a delta positive over there. And I guess that carbon would have a delta positive as well. However, this is a hydrogen that is bonded to the oxygen, so you can form a hydrogen bond. Whereas over here, we don't fulfill the criteria with the hydrogen bond, we just have dipole-dipole interaction. And we see that reflected in the strength of the bonds, because propanol, which only has dipole forces, has a much lower boiling point than propanol, which has the hydrogen bonding. Again, this is all illustrating the relative strength of these intermolecular forces. So we could have the hydrogen here, which is particularly delta positive, could form a hydrogen bond with the lone pair of electrons on another delta negative. Say if it was from the same molecule, you can form a hydrogen bond between those two atoms there. What else do we have under hydrogen bond? We also say that it's also dependent on the number of lone electron pairs. For example, water has a much higher boiling point than ammonia, even though they both hydrogen bond. It's to do with the number of lone pairs. So if I show the hydrogen bonding in water, we have our water molecule like this. We have a lone pair of electrons there, lone pair of electrons there, two H's. We have that nonlinear shape. So what can happen is another water molecule could be there, and we could form a hydrogen bond between the delta positive on the hydrogen and the lone pair on the delta negative oxygen, form a hydrogen bond there. However, oxygen has two lone pairs of electrons, so there could be another hydrogen there, which means that we could form a second hydrogen bond between the delta positive on another water and the same delta negative, but with the different lone pairs of electrons. So we can have two hydrogen bonds here, and that gives us a boiling point of 100 degrees Celsius for water. Whereas with ammonia, we can only form one hydrogen bond per ammonia molecule because there's only one lone pair of electrons. So if I had another ammonia here, how could I draw this like that? We can form the hydrogen bond. Remember, nitrogen is particularly electronegative, and hydrogen bonded to the nitrogen here is particularly delta positive. Lone pairs of electrons, we can form a strong force of attraction here. However, unlike our oxygen where we could form two, because there's two lone pairs, we only have one lone pair over here. So that only gives us a boiling point of minus 33.34 degrees Celsius. So that illustrates that our hydrogen bonding is dependent on, first of all, having the hydrogen bond capacity, and then the number of lone pairs of electrons that it can potentially bond with. Let's see how this is all reflected across our periodic table. We have a few different hydrides here for the same group. So sulfur, beneath that we have cerium, beneath that we have, tellurium, something like that. So these are all hydrides that have that kind of V-shaped molecular geometry to them. And we can explain the trends that we see based on what we know now about our three types of intermolecular forces. So we'd have our sulfur dihydride, would have our SeH2, and then we have our TeH2. Now in all of these cases, we're going to have hydrogen as the most delta positive molecule, most delta positive atom within the molecule, I should say. And then we'll have delta negative, delta negative, delta positive, delta positive, delta negative, delta positive. Now none of these fulfill the criteria for hydrogen bonding. They will all have permanent dipole-dipole interactions. But what we see is that the boiling point of each of these increases as we go down the group. And that's because similar to our van der Waals forces, our dipole-dipole interactions will increase with more electrons. If something has a delta negative, something else has a delta negative, but it's got more electrons, it's essentially got a higher magnitude of delta negative. So that means there's going to be a stronger force of attraction when it comes into contact with a delta positive. So that's what we see here. Increasing the atom size, more electrons, we have stronger forces and consequently more energy needed to boil it. However, if we go to the group just above sulfur, which is our oxygen, H2O, we see this massive increase in the boiling point. And we can explain that with our intermolecular forces as well. Because whilst H2O is very similar, like that, we still have a delta negative and a delta positive, yet we can form hydrogen bonds here because we have our criteria to form hydrogen bonds, and we know that hydrogen bonds here is a much stronger interaction than our dipole-dipole. And that's what we see reflected in the trends of the boiling points. Our hydrogen bonding species is a lot more energy needed in order to boil it because the forces are a lot stronger. Then our dipole-dipole, as we increase the amount of electrons, we increase the boiling point that is observed. So let's just look at this hydrogen bonding in water because it gives water some sort of unique characteristics that are really important for a whole number of things, not the least of which is all of life on Earth. Enthalpy of vaporization and boiling point of water is very high, as we just saw. Due to the hydrogen bonding, these physical properties are much greater than might be expected, as we just saw in that graph in the previous slide. We also see a large surface tension and viscosity that results because of this hydrogen bonding. The hydrogen bonding inhibits the abilities for the molecules to slide over one another, so we have a high viscosity. Viscosity is a description of how thick a substance is, I suppose. Something like honey is a very high viscosity. So because the molecules are unable to slide over each other, because of hydrogen bonding holding them very tightly, we get a high viscosity. And this downward force at the surface of the liquid, again from the hydrogen bonding, results in a high surface tension. And that's why water, if you hit water from a high height, that surface tension can make it as the same as jumping off onto a solid concrete thing. It's a really strong force of attraction. So that surface tension is very high. It's also the reason why you get little water spiders and stuff that can walk across the surface, taking advantage of that surface tension. Finally, we see that ice is less dense than water, which is not what you normally see with other types of materials. Usually the solids are more dense than the liquids because they pack more tightly as they cool down. But you see the opposite in the case of water, and it's again due to this hydrogen bonding. And we can draw it out to show it because what we see happen is that the hydrogen bonding water molecules create a very fixed lattice to form. That's all based on that tetrahedral kind of shape. So if I were to draw this, we could have an oxygen with a hydrogen there, and then oxygen with a hydrogen there, a hydrogen there, and then we could have an oxygen with a hydrogen there, hydrogen there. So I'm not going to worry about filling in all the delta positives and negatives. We know that oxygen's always going to be more delta negative, but we essentially get hydrogen bonds between the oxygens and the hydrogens with the lone pairs that are present. And what we see forming is this hexagonal type lattice where lots of these all form together and we get this very kind of fixed, this very stable hexagonal type arrangement like that. Again, this is only in 2 dimensions, this will be in 3 dimensions. But when the water is in the liquid phase, the molecules are less tightly packed. They can sort of, they're more able to move around and stuff. But when it solidifies, they all sort of spread out and abide by and fit into this very rigid 3-dimensional structure, which sees the density decrease. And that's why we see ice floating on water, not sinking to the bottom, because the ice is less dense, and that has far-reaching ramifications for all of life that has evolved. I mean, if life evolved within water, but if water would freeze from the solid up, it would solidify, and sink to the bottom and then freeze up that way instead of staying on top, which we would see in nearly all other materials, then life on Earth could never have evolved and come out of the water. Just one other interesting thing about this hexagonal arrangement before we move on, this is a really stable conformation that's seen in all over nature, all different sorts of biological things like beehives, certain things in the eyes of dragonflies, certain biochemical molecules and all sorts of chemical molecules. You see this as a very stable arrangement. Things like geological sort of phenomena, the way certain rocks will form themselves. There's just something about the bond angles within this hexagonal shape that makes it a very stable thing that I find a little bit interesting. But that's just a bit of an aside. Let's finish off this whole unit with this last little bit. We have now looked in depth at our intermolecular forces. We've looked in the last couple of videos at our different types of bonding. Let's just link all of the different types of bonding to the physical properties that they exhibit, and that will be a nice tidy bow on this unit that we've done. So, physical properties. Let's look at the physical state at room temperature and the melting boiling point of metallic, ionic, and covalent substances. For our metallic, nearly all are solids at room temperature. If we think back to our metallic model, we have a very strong electrostatic attraction between the delocalized electrons and the cations. This will give generally a high melting and high boiling point. Very famous example of an exception to this rule is mercury, which is a liquid at room temperature, but pretty much all of our metals have very high melting and boiling points. Our ionic solids, solid at room temperature. Our ionic substances have a very strong electrostatic attraction between the cations and anions. Similarly, will give a high melting point and a high boiling point. Our covalent, as we just saw, in general, they'll be liquid or gases at room temperature. Depends on the intermolecular force that is present that we've just looked at this lesson going through. But in general, much weaker than the metallic and the ionic bonds, which will give generally low melting and boiling points. Solubility, so the ability for something to dissolve in water. Metals do not dissolve in water, but some will readily react with water, such as our group 1 or group 2. Our sodiums, potassiums react very violently with water, however, they will not dissolve in water. Our ionic substances, most will be soluble in water because we have our polar water molecules, as we know. We've looked at that quite in depth now. We've got our delta negative and our delta positive. We've got 2 poles on our water molecules. And this can disrupt the attraction between our ions. So if we think to our atomic bonding model, I might just get rid of these other waters. We have the positive and the negative cations in a fixed 3-dimensional lattice. We draw that generally just like this. But what our water can do is that these partial positive and negative charges can disrupt the force of attraction between these ions and essentially break them apart and put them into water. So the water can get in there and can sort of surround each of these, where you would have, how can I draw this? A bunch of water molecules with the negative end forming bonds with the positive ion. And then for our negative ions, we would have the positive charge of the polar molecule sort of surrounding it like that. And what you end up with are what is called ion dipole forces. So the partial charge on a dipole can form an attraction with the full charge of the ion, and it can dissolve it, and the ions will go into solution. For our covalent molecules, this is something we're going to look at more in detail further down the track, but the solubility, you can remember it based on this like dissolves like, where like things will dissolve, like charges dissolve other like charges. So water is a polar molecule, so those with a high degree of polarity will be soluble. Those that are non-polar or have a low degree of polarity will not be soluble. So polar things will dissolve polar things, non-polar things will dissolve non-polar things. Like dissolves like. But like I say, that's something we're going to revisit further down the track in a few lessons' time. Finally, electrical conductivity, the ability for each of these substances to conduct electricity. Metallic, very conductive when solid or molten. Delocalized electrons from that sea of delocalized electrons are free to move and can therefore conduct a charge. So in order to conduct a charge, you just need a charged species that can move, essentially. So in the case of our metals, we have the sea of delocalized electrons. Our ions can't conduct when they're in the solid state, but they can when they're in the liquid / the molten state, because the ions can move and can conduct a charge when they are in the molten state, but not in the solid state. They are fixed in place in that three-dimensional lattice. Finally, our covalent simple molecular structures are not conductive. They have neither free electrons nor free ions to carry a charge. And with that, we finish our chemical bonding unit, Unit 3. What have we done? We've described, interpreted, and predicted the effect of different types of bonding on the physical properties of substances, deduced the type of bonding present from given information, and shown an understanding of chemical reactions in terms of energy transfers associated with the breaking and making of chemical bonds. As always, these are some tasks that you can do to consolidate what we've done. Pause the video, work through those if you so choose to do that. Thank you for joining me on this unit into chemical bonding. I will see you on the next unit when we begin Unit 4. See you then. Have a good one.